Well, I'm Rob McCurdy. I'm an assistant professor in mechanical engineering with courtesy appointments in CS and also EE. And I think, as you'll see in some of the work, it's kind of interdisciplinary, hence the fact that we've got people in my lab from all those different departments. I'm super happy to take questions at any point during this. I also have shown, let's see, anybody see a talk that I gave for the CS Colloquium this fall? Okay, one person. All right, so I'll probably stay, apologies, close to that content, though I'm happy to change it up and show other stuff, because one of the best things I get to do is to show the cool stuff that people in my lab are working on. So if you would like to see other content besides what I'm showing you here, I'm happy to pivot. So just let me know. Okay, so I lead the matter assembly computation lab, and that name is deliberately chosen to be as broad as I possibly can be, to give us some freedom to explore a bunch of different areas. The topic of this talk is organized around bio-inspired design of robots and robot structures. Fundamentally, though, we are a matter computation lab, so we do computational design fabrication with applications in robotics and medical devices and all kinds of other places as well. I like to start my talks with pictures of some of the people who have actually done the work. I kind of advise them and give them directions and some criticisms and encouragement, but they're the ones who really do it, right? So the overall sort of research vision is to try to automate the design and fabrication of robots. Now, admittedly, this is a little bit weird because most people in robotics start with the design. You know, they have a design that they found somewhere or that somebody else has proven is really good. And then they spend all their time doing plant control. And we don't do any of that. We do robot design and fabrication automation. The idea is that maybe by making robots faster to build and faster to fabricate, we can try to make robots more accessible and more tailored to the specific applications that people might have sort of in mind. Have you heard of the dull, dirty, and dangerous mantra for the use of robots? Roboticists talk about this all the time, and that's sort of motivational and inspirational for people. But I would say that we actually, in robotics, have kind of nailed the dull, but really not nailed the dirty or the dangerous applications of robots, except in military applications, I guess, where cost is really not an interest or a concern primarily. And so I think part of the reason that we, as roboticists, have not really engaged much in the dirty or the dangerous is because our robots are precious to us. They take, you know, many person years of time to design and fabricate before you ever wrap a controller around one of the docks. So I think that makes us very conservative as roboticists. And so the hope, the idea, and the inspiration for doing this computational design and fabrication of robots is to break from that mold and allow our robots to be more tailored, more custom, and actually used in the world. So yeah, the vision is to enable robots that actually walk out of the printer, though, of course, that's inspirational. I've approached that in some examples, though never a complete robot with batteries included. I think, though, along for the ride with this vision for having robots that can be designed and fabricated automatically is the potential to really democratize electromechanical engineering. So who's built an electromechanical system before? Right, many folks. I think that if you observe and sort of reflect on what you've done in that process, you know, you formulate a potential solution, you spend a lot of time fabricating that solution, you might spend a lot of time just becoming really familiar with where to get the stuff for that solution. And often the mark of a good roboticist is someone who really knows how to shop well. And that's kind of crazy, but it's also, in my experience, and I think in the experience of many others, true. You know, finding the right component can make or break a project. So I think that we often lose people, particularly people at the beginning parts of their careers in electromechanical systems design, just because it's hard and you have to be a master of many different topics, including shopping. So part of the hope here is that in the process of making robots computationally designed and fabricated, we can also lower the barriers to entry. And so I love this old video of someone who sounds like a teenager based on the audio, designing this giant robot spider in Minecraft. And I don't know if this will play again, something's going on here, here we go. Right, so Minecraft is a workspace that was never intended to design and fabricate robots, in this case, simulate robots. But people figured out how to do it. And I think part of the reason they figured out how to do it is because it provides a user-friendly interface with rapid feedback about the success or failure of a particular design. I would say robotics is the opposite of that. You might get feedback once a year or once every 5 years. So I think we might want, as roboticists, to work to try to change that feedback mechanism a bit. And my hope is that by pursuing this dream of automating the design and fabrication of robots, that we can also, along, with all the other things, make it more accessible to people, try to extend robotics to other folks. Okay, so with that as prelude, I'll reflect on some of the amazing robots. And now my Atlas image is a bit out of date because they've gone through several more revs. And now they have a wonderful new, fully electronic brushless DC motor powered version of Atlas. Though my point is identical, which is that these are sort of the high watermark of robots in the last 10 years, fabricated by people and designed by people. And every one of them required an unbelievable amount of design expertise and effort, and in fabrication expertise and effort. So it's because these are complex systems. They're incredibly complex systems that require people to have expertise across many different domains in order to bring all that experience to bear on this problem. And as I said, indeed, sourcing these things is an unsung challenge, I would say, in robotics. And sometimes that's just, yes, knowing how to shop. Sometimes that's knowing how to fabricate things, design things and fabricate things. One of the challenges in this realm is that it is truly an arbitrary design space. You can make anything that you can imagine, which is great, but it also means, how do you wrap your mind around that design space? How do you perhaps apply computational tools to try to accelerate your design process? I guess I'll stop for a second and dwell on this. Has anybody heard of topology optimization in the audience? Yeah. Okay. So topology optimization is one approach that people have taken to automating the design of a mechanical structure. And very briefly, the idea, and by the way, as prelude, I'm saying what topology optimization is because although there are parallels between what I'm about to show you in this talk and topology optimization, I'm not going to show you topology optimization itself, right? But topology optimization, TO, is the idea that you've got some design space, a prototypical lump of material, the clay that you can use. You apply loads to it, and you apply constraints. For example, make a material that under a particular load, make a design, I should say, that under a particular load deforms as little as possible and weighs as little as possible. That's the classic compliance minimization problem in topology optimization. That approach, that formulation, has been studied by loads of people going back to the late 90s, and there's some wonderful results in that area. And it's one approach to trying to figure out how to distribute matter in a design to satisfy a set of objectives and constraints. I'm going to show you in this talk some other approaches to that. All right. So, right, I already give you the prelude to the dull, dirty, dangerous, right? And so this is my motivational speech. So the approach that I take in thinking about how to solve this design challenge is to discretize the world into a series of repeated unit cells. So imagine that your robot is just a bunch of voxels. Now the challenge of designing that robot is simply an allocation problem. What material goes into which location, right? So that's straightforward, I suppose, though as you'll see, there are some challenges. And the quick answer is yes, although it's a straightforward way of discretizing the world, the number of options that you could potentially have in assigning those materials is larger than the known or estimated number of atoms in the universe. So it's a huge design challenge, even though we've made it discrete. But I just want you to hold that in the back of your mind, that this is effectively, this design challenge for robots can be viewed as a material allocation challenge. Then the question is, how do we allocate that material? How do we decide what material goes where? Okay, so far so good? Mm-hmm. All right. So if we're gonna use this design approach for designing robots, we have to at least solve these 6 different challenges. So how do we provide systems that provide signals and sensing? How do we design and fabricate systems that are low-level controllers and wrapping, say, a PID controller around some DOF? How do we design and fabricate systems that can do higher level planning, commands, behavior? How do we design and fabricate structures and mechanisms? How do we design and fabricate actuators? And how do we design and fabricate systems that can store and transmit energy? So let's get past this. I haven't solved all these problems. Perhaps I never will solve all these problems, but this is how I'm organizing the work that we're doing toward this end goal. All right. I also want to ask a question. Has anybody in the audience taken electrical engineering classes? Anybody? Okay, right. Anybody in the audience ever used any kind of VHDL synthesis tool? Cool. What was the platform that you were using it for?
It was digital design classic. It's been a while.
But you were trying to basically figure out.
Quartus or something.
Right, yeah. So you're trying to solve an allocation problem for a resource on an FPGA,
Yeah.
right? So FPGAs are field programmable gate devices, and I guess the A is arrays, right? And the problem is you've got all these resources on an FPGA, a whole bunch of very low level, think of it as logic blocks. How do you arrange and connect all those logic blocks to then implement some software that you might write at a higher level, in a higher level language, maybe C or C++, or some other intermediate language, Verilog, VHDL, something like that. So the electrical engineering community has, over the last 50 years, solved many of the problems that I'm alluding to in the mechanical design space. They figured out how to allocate resources, standardized resources, to solve problems by making compilers. And so part of my message, as you'll see later on, is that we need compilers in the mechanical or the electromechanical design domain. And the fact that we don't have those is a bit remarkable, because I would say that today, when a mechanical designer sits down and tries to solve some mechanical design problem, they're solving that problem in much the same way that they did 2,000 years ago. They're drawing. They're using their intuition, their experience, their knowledge, and they're drawing a solution. And then, yeah, we're leveraging tools to do simulation to try to accelerate the round trip before you fabricate something, but it's more or less the same kind of thing. So I think that we can reflect on what folks in the electrical engineering world have done to kind of motivate where we might need to go in the mechanical or electromechanical design domain. So you'll see flavors of that as well. All right, so yeah, I mean, my lab focuses on tools that can automate the design and fabrication of these electromechanical systems. All right. So I've already said some of this stuff, right? We focus on answering the question, where do I place the right material to get the behavior that I want? All right. So today I'll show you a couple of examples of addressing a few of these 6 different problems, right? So we'll focus on, let's see, signals and sensing and structures and mechanisms. And so this first one, we'll talk about developing design automation tools for structures and mechanisms, or think about it like the robot body, right? So as I said before, I haven't made life dramatically simpler for myself by discretizing the world into voxels, because now I have potentially billions of voxels, each of which might take a small number, maybe 10 different allocations. And so if you compute the number of options where replacement is possible, it's basically 10 to the billion, for example, right? So it's a huge number of options. So we can't solve it directly, but I'll show you an example of solving that or addressing that using evolutionary inspiration. So with this work, which is a bit older now, but still I think serves to motivate what we're doing, we drew inspiration from Drosophila. And so during its developmental process, the Drosophila has this challenge. Which cells should become the thorax? Which cells should become the wings? Which cells should become legs? And part of the way that it solves that problem is by using a chemical gradient, so these morphogenic gradients that show up in the body of this developing organism. And so in fact, what you're seeing here are the colors. The colors of these cells, those little dots, are literally the cells inside the developing organism. The colors of those cells correspond to the concentration of a particular chemical, which has a concentration that varies along the length of the robot. So the thing to keep in mind here is that we've got a signal, which is a chemical concentration that's proportional to the location in the body, right? And so that's the way this organism is using to figure out what cells are going to differentiate and develop. I should say what sort of prototype cells are going to differentiate and develop into the ultimate cells that make up the body. So we use that same inspiration in an evolutionary context. Now, obviously, here are the differences. The differences are vast. One is that I'm writing a function. In fact, I'm not writing a function. I'm writing code that writes a function. So think of that function like that morphogenic gradient. The function takes into its inputs the XYZ locations in this body, and it gives as output what should be at that location. So it solves the material allocation challenge. What material goes where? Great. The problem is, how do we come up with that function? So we use evolution not to design the organism, but to design the function that designs the organism. So this is a so-called generative approach because we're developing the generator algorithm for this. That might seem convoluted, but the advantage is that now the search is over the space of the size of the function rather than over the space of the size of the organism. So we can have fewer parameters that we're searching for. And if you've taken any classes that look at evolutionary optimization, or if you've done it yourself, one of the problems is because it's a gradient-free method, you don't have rapid feedback about how to change the design that you have. So it behooves you as a user of evolutionary algorithms to make the search space as small as possible. One other trick that we used in this work was that the function doesn't stay the same size over the course of evolution. The function actually starts out very, very small. We represent the function as an acyclic graph, so a directed acyclic graph. Initially, there's only one node in this graph. And there is a one-to-one correspondence between a DAG and the string version of the function, right? If you're just writing out the function. So we can use graph operations to insert nodes into edges or to add new edges to this graph. And in doing so, modify the function. And over evolutionary time, we complexify, we add additional nodes or clauses to the function. Okay? I'll show you a video in a second that shows the progression of this. The last thing to know is that we're rewarding individuals and therefore rewarding the functions that generate the individuals for two things. So it's a multi-objective search. We're rewarding them for how fast they can run, and we're rewarding them for being lightweight. The idea being that creates a nice Pareto space where there are trade-offs. You'd think that organisms that are really strong might be able to run really fast, right? But you might want things to be lightweight because they might consume less energy per unit distance traveled. And so who's ever used a multi-objective approach in optimization? Anybody? Okay. One of the things that works well is to have trade-offs, because if you think about what you do as engineers, it is the study of making trade-offs in design, right? And so anyway, so that was the setup to this particular work. We had 5 different materials we could allocate. Nothing, void space, and then these 4 different materials. 2 kinds of muscle that are antiphase with each other, and then a soft and a harder material type. So here's some of the individuals that came out of this evolutionary run. Part of the reason that there is diversity in this, and I'll show you a bunch of different organisms, is explicitly because we were using a multi-objective search. So there was no one right answer. And I would challenge you that that's really the case in engineering all the time. There is no one right answer. In fact, usually during a design process, you're discovering new constraints and objectives all the time throughout the process of your optimization. So why not use computational approaches that also reflect that study of trade-off? So you'll see that we do Pareto optimization very often in the lab for that reason. So in the interest of time, I'll skip past this. I can come back to it if you like. But this was just looking at, this particular part of the video is just looking at how these individuals progressed over evolutionary time. And there's a lot more to say about evolutionary approaches, if you like. Okay, so the takeaway in this work, was there a question?
Yeah.
So, yeah.
Did you start with any initial constraints on shape, size?
The only initial constraint was that we were limiting ourselves to a 10 by 10 by 10 voxel world. And the initial organisms, the initial generator algorithm had just a single node in it. That single node, I kind of glossed over this, but there are a variety of different node types, sort of pictorially illustrated with these little images inside the nodes. But we had Gaussians, square waves, sawtooths, sigmoids, etc. So many more activation functions than are typical in a neural network. We just kind of threw them out there as options for the algorithm to choose from as it inserted these node types into the graph.
And each cell has physical characteristics, their animations, for instance, like what would differentiate a bone cell if you build a muscle?
Yeah,
Is it just X, Y, Z, like how did
so
you?
they're volumetric things. The two muscles work in antiphase, and it's a very simplistic actuation scheme. They just change by 10% volumetrically. Energy be damned. So we never fabricate these things for that reason. They're actually, there's really no great way to fabricate these. A few folks in later studies have used pneumatics to try to inflate voxels. And they get designs that are kind of like this, but part of the reason that these are so dynamic is that they are not energy constrained in the actuation, right? So this was simulation only. Bone versus soft were just different elastic moduli. Yeah, very simple material models, yeah.
Just a really quick question. Thank you for the presentation so far, very interesting. Long story short, you're doing an optimization. I'm just interested in understanding whether there's a real-time component to that optimization, an iterative component. If those objects that you created had a sort of a evolutionary input each time you iterated through, did you ever go down that road with this simple solution or this simple example?
Let me know if I'm on track to answer your question. So this is these population-based methods.
Soul seeking.
Yeah, I mean, so the objectives, all individuals were scored along these two dimensions, along how far they moved during the fixed simulation time, 30 seconds of simulated time, and how much they weighed. So those were two components of a multi-objective Pareto-based optimization. Now, because it was a Pareto-based optimization, we never combined those two different things into a single scalar measure of goodness, because that then collapses you to search along one direction through your multi-objective space. So there is a Pareto approach, population-based. In this case, the population size was 30 individuals. We use the NSGA2 algorithm style. So that has internal approaches to maintaining diversity in the population that tries to spread the population along the Pareto front. So we try to maintain individuals in every population of 30 that were fast, kind of on the extreme of being fast and on the extreme of being lightweight, which is why you see in the population at the end of 1,000 generations, which is where we stopped it, you see individuals that are both large and small and fast and slow.
Thank you for that.
Yeah, yeah.
Did muscle group 1 and 2, where you contract and expand and contract, did those weigh the same?
Yes, yeah, great question. Everything was the same density and
Same
therefore the
flow.
same mass. Yep,
Muscle same. Okay.
Yeah. yeah. So the only way they differed was in how flexible they were.
And so just one quick one, and again, there was no a priori information loaded into this, it was just governance.
That's right, yeah. Right, so the 30 individuals in the initial population had the same number of inputs and outputs as all the generator networks do. They have X, Y, Z, and then they have another input, which is basically distance from center. And we found that yielded individuals that we found more pleasing, right? So that was our kind of putting our thumb on the scale of evolution. But otherwise, they all had the same number of initial nodes, which was 1. And that initial node could have been a Gaussian, could have been a sawtooth or a square wave. That was up to random chance. And each of the nodes also has a bias term, and that bias was also set via random chance. Yeah, so they weren't all identical, but they were all equally simple at the start. Yeah.
It's interesting how even without any like prior data, you still got simulations that looked like a snake or like a starfish or like actual real natural.
Believe me, we were thrilled. Yeah, I mean, I found that in the simulator, if I manually designed things, I could manually design things that ran, things that walked. But frankly, my designs weren't able to exploit the dynamics in the same way that the optimized designs were. Mine looked much more sort of, I don't know, uneven in their walking, right?
We need to see iteration though, let's see kind of that evolutionary biology.
Yeah, well, maybe I shouldn't have skipped past the video. I mean, I can show you, you get a sense of, let's see here. Let's go to here. Here we go. Okay. So this is looking at one of the top performers in a particular niche. And again, there's an idea of niching in evolutionary optimization across generational time from 0 to 1,000 generations. And so you see how this particular lineage developed its ability to run, basically by developing what look like legs over time. And so I'm only showing the distance score here, but of course it's being scored along 2 dimensions at the same time. Yeah,
Have you ever considered playing around with like not a flat surface?
for sure. In fact, we did have, in this paper, I made a surface that had concentric rings. And so the individuals that evolved had like little teeth-like features that would allow them to kind of grab the rings and pull themselves over. Yeah. Yeah. Cool, okay.
Okay.
So let's,
How long did it take the process?
30,000 core hours.
Yeah, it's sort of, wow.
Whoa.
So scaling that.
So-
is exponential.
Yeah, I mean, things have improved a lot in the time since we did this. So the simulators are much faster. One of the challenges at the time was, these are still challenging structures to simulate because they deform a lot.
Mm.
So they have a large geometric deformation. Typically, in a finite element context, large deformations are problematic because what happens is that your elements stretch out. And the aspect ratio of your element might go from this to this. An element like this is less stable from a simulation perspective and less accurate. So the usual trick in the FEA community is to remesh. So if you have a structure that does this at some point during your simulation, you then break it up into a bunch of other sub-elements that are better behaved. But that remeshing process is slow. Contact is typically an inextricable part of these kinds of soft deformable body simulations. And contact is a tricky thing to simulate as well. So at the start, I mentioned topology optimization. There are some early efforts at extending the ideas of topology optimization toward designing soft deformable structures that are contact rich, but it's a challenging scenario to simulate. But the future of this work will involve developing gradients of one type or another. And when I say gradient, I mean, I've got this design space where I've got, voxels. The voxel at location 111 might be one of 5 things, right? I would love at every one of my voxel locations, in this case, 1,000 locations, I would love it if I had some function that gave me the partials of the objective functions. How fast can I run and how light am I in terms of the design variable at that location? Should I make this thing a little bit more empty? Should I make it a little bit more red, a little bit more blue? So that over time I can then push those designs. We don't have differentiability in the sense of the objective functions with these kinds of simulators. These are just forward only. But there are folks, including folks here on campus, who are developing simulators that are differentiable in the sense of the objective functions. So you get the partial of how fast it ran in terms of every one of the design variables, which is great if you can get it. Yeah.
I know you mentioned some people are working on trying to create something like this with a contracting and expanding. What type of material in theory would you love to use for something like this if you were to physically fabricate?
This is the hard thing, right? So I don't know any materials that, other than waxes, like thermal phase change waxes can expand the most up to about 17%. Water's volumetric change during thermal is what, 1%, less than 1%, something like that. So there aren't a lot of materials that expand and contract volumetrically. So people have made, so Josh Bongard, who was a previous member of Hod's group where I did my PhD, now a faculty member at the University of Vermont, people in his group tried to make inflated voxels with some degree of success, and they had a nice paper on it. Fabrication is a challenge. You can use 3D printing. At the end of the day, though, you're pumping air into and out of this large structure. So you've got this fluid flow that has to go through a hose. And so you have a tethered robot. And my dream is to have truly untethered robots, things that are autonomous and can move around the world. And so we haven't, in my lab, invested a lot in approaches that inherently need to be tethered. Yeah.
This is probably an ignorant question, but it reminds me of 3D printing like muscle cells and like skin cells and all that.
Yeah.
Would that ever further down the line be a possibility?
It is. Yeah. So there are these xenobots that, in fact, Josh's group is associated with. Josh Bongard's group is associated with. And they call them xenobots. They are, at this stage, to my knowledge, not 3D printed, but manually assembled collections of cells based on frog cardiac cells, and they kind of quiver in synchrony based on where they're placed. So yeah, it's an interesting area. You had a question?
Just a sort of context question. You mentioned finite element. Just really quickly, the finite element analysis you were doing to simulate these, did you use any other, types of analysis to, geographically, if you will, do optimizations differently? I was just sort of curious.
In terms of the simulation that we used for this?
Yeah, yeah.
Yeah, so it wasn't an FEA approach. This was based on a different idea that was sort of, you'll find it in the sort of design and simulation community, there are folks who skew much more toward the high mechanical fidelity realm, and they focus on making very wonderful continuum models, usually using the finite element method. And there are folks on the other side who are really skewed toward making things that look great, and but also are efficient. So those folks usually are more in the computer graphics community. And a lot of those simulations are based on particle methods, where it's somewhat difficult to make a particle-based method faithfully represent the physics of a body like this. We used in this work something kind of in between. So there was a point mass at the center of each voxel where all the mass for the voxel was collected. And then there were flexible beams modeled as Coursera rods that went out to the faces. And those beams then connected with an adjacent voxel that was next to it. So you got two Coursera rods basically fused like that, right? And so it's straightforward to describe the forces and deformations on a Coursera rod. So that was the way that, and they can bend and twist, you don't have the same numerical instabilities that you have with finite elements. But, because it's an aphysical description of a voxel, we didn't truly sort of faithfully represent the physics. We did create something that looked about right.
Very interesting, thanks.
Yeah.
I should probably just offer, there's a lot of work that's been done in the biomedical world about, muscle cells. And you can easily have a network of electrical stimulation. That's definitely something that would be doable these days.
Yeah. And there was some follow-on work to this that I wasn't involved with, where they took inspiration from this kind of work from what I understand, and effectively modeling each of these voxels as a cell that could pass a time-varying electrical signal across its surface. So then we had cells with signals propagating across them with time delays, and then the authors of that paper coupled those signals into the actuation signal of each of the voxels. So you get these kind of quivering bodies that incorporated the control as part of the design process, where in our case, the control was just a central pattern generator where every cell actuated either at 0 phase or 180-degree phase. All right, let's see. So we are at
The risk of
12 o'clock.
time, you gotta walk before you.
Well, I mean, maybe this work is contrary to that, because these things came out running.
Well, there's some questions from online
Good,
on
yeah.
the text.
Let me take a look. Okay. Yeah, so somebody asked about Daniela Roos. I did my postdoc with Daniela, and so that was definitely, inspirational for me. So yeah, I think it's, I completely agree with that impulse. The question was about what do I think about Daniela Roos's work in writing a robot compiler. And I think that that's exactly right, yeah. Somebody says, do I only work in the simulation space or also collaborate with folks that test the simulations in tangible objects? Let me show you some slides where we do fabrication of tangible objects, because we do both in my lab, yeah. Somebody said, can I explain more about why and how I combine these activation functions? What I'll say about that right now is that we allowed evolution to choose from this palette, a limited palette of activation functions. So we didn't try to prescribe which function was going to go where. We just said, hey, optimization, you've got, I think in this case, 8 different activation functions to choose from. Go. All right, so let's see, where are we? Okay, so yeah, let's talk about some tangible objects. One of the areas that we're excited about is soft robots, trying to make soft, squishy objects that can do something. In part, I was motivated by the frustration that we were never able to actually fabricate those voxel bots. And so I wanted to actually fabricate things that were real. This is my depiction of the current state of the art, even today, in the soft robot design and fabrication space. So you have people who work with CAD tools. So you will interactively draw something with a CAD tool. You'll then export some drawing, often as a surface model, into a finite element tool or equivalent to be able to model what that one particular design is going to do in response to inflation pressures and external contacts with the world and so on. And then you'll usually embark on some kind of multi-step, hands-intensive casting process to fabricate an instance of the thing that you just validated via simulation. So there's a fairly long design, evaluate, fabricate, and iterate loop that folks go through in either the soft robotics space or, this is, I would say, typical of many conventional design, sim, fab, evaluate loops. What we're trying to do is to reduce the loop times. We want to make, we're not getting away from iterations, but we want to try to make this loop go faster. And so what we're trying to do is to integrate together, which is why I have all of these three items in the same overarching block here. We're trying to integrate these things together so that users, or in some case agents, not users, can go around this design loop rapidly. So I showed you in the previous work an instance where an agent went around that design loop rapidly, except that we never exposed those designs to the real world. And so here we want these designs to be exposed in the real world. So we're going to have to confront a classic problem in simulation and fabrication, which is the so-called sim to real gap. You simulate something, you test it in simulation, then you fabricate it, you test it for real, and you get differences in how closely those things correspond. And that sim to real gap is a problem, if we're trying to use simulation to go around the design loop faster. All right, so let me tell you a little bit about how we approach this integration challenge. What I'm showing you here is the other side of the network-based representation that I showed you in the previous slides. Remember, I said a minute ago that there is a correspondence between, let's see, I'm not showing it yet. There's a correspondence between a string-based formula that represents a shape and a directed acyclic graph that represents the shape. They mean the same thing. So what we're doing here is we're evaluating this formula, which may seem a bit inscrutable, but we pass in this case, theta and phi, theta and z in this case, and then we get out a scalar value. Then we draw a so-called level set or isosurface through this scalar field. So it's some volumetric space where at every location I've evaluated theta and z. And then and also R, which should be in there somewhere. There's R. And I get a number at every location in three-dimensional space. And for all the numbers that are the same or the same within some epsilon, I draw a surface through them. So for the surface that equals 0, where all the zeros are, I'm going to use that surface to represent the surface of the object that I'm trying to represent. All right. It's a weird way, perhaps, of thinking about representing design, but there are some advantages, and I need you to just trust that there are some advantages. I'll show you some advantages. Okay, one advantage is that I can rapidly scale these devices just by taking isosurfaces through numbers that are not 0. So I can expand it or contract it by saying take an isosurface through 1 or through -1. I can compose these functions together with small perturbations. So for example, the design in the upper right is maybe 1 finger. I can then compose, in this case, 6 of those by simply applying a coordinate transform to one of the inputs, in this case, theta, and now I get the starfish-like thing. The real reason that we do it this way is, who's ever used SolidWorks or some other interactive design tool, right? Who's experienced when you parameterize a design, the design doesn't compile problem? You've seen this, right? You change the design enough that a feature that was driving something else goes away, and all of a sudden, poof, your design goes away and you can't do anything with it. That kind of event would happen all the time if we were using an algorithm to drive those parameters. So we need representations of the design that are not sensitive to those kinds of changes. And so this style of representation, which by the way is basically the same style of representation I showed you in the last segment, is not sensitive to those kinds of parameterized design changes. You'll always get a design. It might not be useful, it might be disjoint, but you'll get something which we can then run through the next stage, which would be the simulator. Okay, so yeah.
Really quickly, this characterization of the scalar field approach, pretty easy to apply to any kind of geometry. Is there a formulaic approach to using this characterization as opposed to the other AI sort of optimization?
I think so, yeah. I mean, it's a little bit different in thinking about, in fact, there are commercial tools now that use an implicit representation, which this is an implicit representation of a geometry. And they allow the user to interactively create designs, just like if you were using a conventional CAD tool like SolidWorks. You draw something, you extrude it, you cut it, whatever. But the underlying representation is an implicit function of the object. So to the user, it looks like you're doing the same things, but one of these tools is called topology. And topology allows you to, I think there's a reactor right there. You're fine. Just beware. And topology allows you to then create a function-based representation of the design, which makes it robust in this kind of way. Though we're not really heavy users of interactive design tools because we want the designer to be an algorithm rather than a person.
Right.
Yeah. Okay, so some other reasons why these implicit representations are powerful. I'm showing you on the left-hand side a published result circa 2020 of a soft bellows-based actuator, 3 different discrete actuators where they inflated and then they bent in different directions. On the right-hand side, I'm showing you our rendition of that. These designers on the left did not use implicit representations. Here we have discovered implicit representation that created one of these objects. And the nice thing about the implicit representation is that we can create this whole continuum of different designs by changing one parameter. So notice that we're going from 1 bellows structure initially to 3 bellows structures just by sweeping through the modification of a single parameter. In this case, where we drew the level set through the scalar field. So it's a powerful representation of geometry. It's quite expressive. And that's a nice thing because if you reflect back to what I said at the beginning about evolutionary search, you'd like your search space to be small. And yet you'd like to be able to represent lots of different geometries. In this case, I'm showing you the result of just changing a single parameter continuously, which yields dramatic differences in the shape and topology of the object. That's a good thing. All right, so here I have this double-headed arrow, which I was searching for. I should have reorganized the slide. The double-headed arrow represents the one-to-one correspondence between DAG and string-based representation of a function. I personally find it easier to look at the graph rather than the string. It's just the way my brain works. So, and I would say that we tend to operate on data structures as graphs rather than as strings. Maybe because of my bias, I'm not sure, but you know, we can add edges, we can delete edges, we can add nodes, delete nodes, modify their parameters, etc., to change the string, which then changes the structure. And on the right-hand side, I'm simply showing you the effect of sweeping through 1 or 2 different parameters with the same representation, just to reinforce the point that it's a very expressive way of describing geometry. And this slide is meant to show basically whoops, I went too fast. Basically the same thing. All of these different shapes are represented by the same simple DAG with different parameter choices. So it's a very expressive, though I would admit, inscrutable design space. So we're trying to make it a bit easier to navigate. We've made this interactive design tool that's a MATLAB IDE that allows users to interactively add nodes and edges to a graph and then immediately see what the surface looks like that's generated from that. I sort of tested the hypothesis that this could be used by having an undergrad who was completely unfamiliar with any of these ideas, just play with the tool for an afternoon. And the approach that I think worked best was for that person to just not have a particular objective in mind, just explore and develop intuition for what the connections were between the design space and the realized space. So the graph space and then the object space. Once that person developed those connections, then they could learn from that and grab certain subsets of the graph and then apply them. So for example, if we wanted to make a structure that was more like a finger where there's repeated units and they were on one side, they found that like this little region over here was what created each of the individual bellows, and then the region on the right was the thing that created the repetition with or without variation. So they could then compose graphs and get the thing that they wanted. So I'll show you some other examples of that. Oh, I should, before I move on. So in parallel with having a means of evaluating a graph and then showing you what it looks like statically, we also implemented a connection to a finite element tool so that users could deform them in response, in this case, to inflated pressure, because we're making these soft bending actuators, which are typically inflated. And so we allow the users to rapidly evaluate what they do in response to deformation using a tool called FEBio, which was actually designed with a biomedical application in mind. It's used extensively for trying to simulate surgeries. And it's good for us because it can simulate hyperelastic materials fairly accurately, but it's also open source, so we can incorporate it into this tool. So there are a couple of tricks when applying FEA. One of the tricks is to use the right representation for the right challenge, and there are so-called shell-based elements and also volumetric elements. If you use the shell-based element, you get a much smaller simulation in terms of the number of degrees of freedom you're trying to solve than if you use a volumetric-based element. So this is just a comparison between the two, but I'll skip past that. Here we're comparing some, I would say, somewhat complicated objects. We're comparing their deformation in response to an internal pressure when simulated with volumetric elements, which is our kind of our gold standard, versus shell-based elements, which are about 10 times less compute intensive, just to show that these are more or less the same. And these next slides are meant to show that, you know, we can make structures, we can design structures and simulate structures that are similar to things that have been published elsewhere, but then go beyond things that have been published elsewhere simply by iterating on these graphs. And because we have this interactive design tool, it's quite quick to make these graphs and then simulate these designs. So you get a whole family of different designs that in graph space look very much the same. But if you're starting from a perspective of imagining a solution and then fabricating it via casting and then testing it, it might take you months or years to come up with a design. You know, you get these really weird looking things, which may be useful for something, right? I don't know. This is, you know, meant to be sort of inspirational for like the canonical starfish soft robot, right? Okay, so let's bring it back to optimization. So what I showed you before was a sort of human-driven interactive exploration, but we want to use these optimization tools. If you want to use optimization, you have to create metrics that you can evaluate. So we created a couple of evaluation metrics. One was how compliant is a structure? The inspiration here is we want things that are soft. The whole reason you make soft robots is because you want things that are soft and compliant. But you also want things that are forceful. You'd like to be able to, you know, pick up an object with a soft actuator. So those two things are kind of in tension. Again, they create this nice, almost, well, I wouldn't claim orthogonal, but different set of objectives in a two-dimensional Pareto space. So we're going to have things that are compliant and things that are forceful. And you might not have things that are both compliant and forceful. You might have something that's really forceful, but not all compliant. And something that's really floppy and compliant, but not all forceful. So far, so good? All right, so I'm not going to belabor the explanation of these functions, but we came up with these functions which were meant to try to avoid cheating in optimization, which is a common problem. By cheating, I mean your algorithm will exploit something that you didn't think carefully through in your objective metric, and will give you something that isn't the thing that you want because it finds the weakness in your logic. So it took us a couple of iterations to come up with functions that didn't immediately exploit our logic of what we wanted. So that's the setup so far, okay? One of the things that we also wanted to do was to score other work along these metrics. So we went back over the last 15 years in the soft robotics world of soft bending actuators, and we tried to score all these other papers along these two dimensions of force versus compliance. So you can see all of the circular dots, different color circular dots with numbers, are published works along these metrics. And then the squares are the simulation results from our work from this particular experiment that only took us a weekend. So the upshot is that in a weekend, we were getting designs that outperformed many other designs in the soft robotics world when scored along these two metrics. Now, in fairness to the original authors of these papers, they didn't have these metrics explicitly, but everybody in the software robotics space has the same kind of objective. They want things that are compliant and they want things that can do work on the world. So I show this plot to kind of inspire the use of computational tools in this particular space. Now, admittedly, we're not out at the Pareto frontier, right? If you're out at the Pareto frontier, we'd be out here. And so there's work to do. Now, you may ask, you're showing lots of simulation results. Did you fabricate these things? And the answer is yes. So that one that's in the green box is actually a 3D printed version of one of these results. And you can see a little arrow. The arrow is my admission that we don't completely have perfect sim to real correspondence. So we do change a little bit in our forcefulness and our compliance when we go from simulation to fabrication. And that's due to a couple of different factors, inexact material model, and the fact that our fabricated objects don't have really, really thin skins like our simulated objects do. But we're doing pretty well there. And we can do better if we then use the more expensive simulation that's volumetric based rather than the cheaper shell-based element model. Let's see, so we are at 12:20.
Yes.
Let's see. We're gonna finish in 5 minutes, right? Or less.
Sure.
Okay, then let's go somewhere else. Okay, I want to show you this. So this is something I'm pretty excited about. Who's used OpenSCAD? Anybody use OpenSCAD? Okay. Somebody asked a question about compilers. Now there's a bunch of questions in the chat, which I'll come back to in a second. OpenSCAD is a open source compiler for designs that uses a boundary surface based representation. So the idea is that you write a script and that script gets compiled into a surface. It might be a whole bunch of disjoint surfaces, or it might be one continuous surface, but everything inside of the surface is your object. Now you might have two concentric surfaces, so then everything that's between those two surfaces is your object, but fundamentally you're representing volumes with surfaces. That's fine when everything that's inside of your object is the same material, whether it's one material or some composite. But these days we now have multi-material fabrication approaches that allow us to precisely place different materials at different locations inside of an object. And if you use a boundary surface representation, you have to have a separate surface for every different material instance inside of your object. That's a huge problem. So we created OpenVCAD to address that. It's also a compiler, so it takes as input a descriptor of your geometry that's a text file. Then it compiles that object into, surprise, surprise, a directed acyclic graph. And then we can sample from that graph at any resolution that we want when we want to export that geometry to be 3D printed or otherwise fabricated. So the export process is specific to the type of fabrication modality that we're using. In my lab, we use a lot of multi-material inkjet 3D printing, but we also use a lot of multi-material extrusion-based 3D printing. It also works just fine for representing objects that are fabricated with a single material, though I wouldn't say that that's the highest and best use of OpenVCAD. But I'll show you some of the features that it has that are appealing for us, maybe for you. So let's go past this. This just says the same thing I already said in words. This is one example of one of these graphs. So you build an object up from a bunch of primitives in a way that's perhaps analogous to what you might do as a user of interactive CAD tools, where you have a bunch of sort of atomic operations on an object that complexifies that object as you develop it. The same is true in OpenVCAD. So in this case, we're achieving this object on the top by composing it from conic section and a sphere, which is then affine transform, in this case, just translate, and those two things are merged together. And then we have an operation that we call F-grade, which is just a way of applying a function that defines what material goes where in a particular design domain. So in this case, it's just grading between the blue material and the green material, if you could see that color change, although it's not very large. Here's another example of an object that is somewhat complex, but has an incredibly simple representation in OpenVCAD. So we have the difference between a cube and a sphere, creating the shape. And then we have an allocation of red and blue materials with 20% probability of being red and 80% probability of being blue throughout the resulting volume. It can also be deterministic. And if you want it to be stochastic, you can also seed it with a deterministic generator so that you always get the same random object. Okay, so let's move past that. Here's another example of merging a conventional boundary surface representation in the form of an STL. So we can import a boundary surface mesh, and then we just fill it with some materials that we want using the functional grading node. And then we fabricated this thing using a Stratasys polyjet system, because I don't get into it. I can talk about it afterwards if you want, but multi-material inkjet's a great way of putting different materials in different locations with high resolution. All right, so we'll go past that. Too many animations. Okay. Because it is functionally driven, it's quite easy to represent very complex geometries when they have a nice closed form functional description. So gyroids are a wonderful example of that. What you couldn't do with other tools is to represent a gyroid, which then has these material gradations between two different regions of the gyroid. We have the ability to create lattices. Everybody's making things with lattices these days, and so we added that functionality in. I mentioned at the top something about medical models, and I'll show you in a second an example of using OpenVCAD to process medical models. Anybody ever confront convolution in your math classes? So convolution turns out to be a really great way of doing blending between different regions. So if I import 4 different regions as boundary surfaces, and then I have a problem, how do I create a grading across those regions when I don't know where the intersections of those regions are a priori, unless I want to exhaustively traverse all of those regions and decide, which I don't, because then I have to compute normals to go across the boundary. It's just a mess. Instead, if you just apply a convolution filter, in this case, a volumetric 3D filter to your input data, which we do functionally and only sample afterward to avoid some problems, you can very trivially describe gradings. You can also trivially describe erosions and dilations and other kinds of affine transforms. The kernel in the convolution is up to you. We have some suggested kernels if people want to use them. I'll skip past how convolution works, just in the interest of time. So, as I said, one of the applications is in processing medical scan data. When you go to a CT scanner or an MR scanner, the doctor radiologist gets out volumetric data about your body that corresponds to the perceived density of your tissues with a particular scalar value in each voxel. And these voxels turn out not to be cubic voxels. They're sort of like long, weird box-like voxels. OpenVCAD allows you to process that. And one of the things you need to do is to remove noise, apparent visual noise from the object. And one very easy way of doing that is simply to apply a smoothing filter implemented as a particular convolutional kernel on your data. And then you can go from left to right to get rid of some of those, the noise speckle. And so you can print these things. Let me just, let me conclude there. Yeah. Oh dear, now somebody said we cannot see it.
I think it's okay. You
Okay,
can skip
all
to
right.
the last one. Sergio is asking, is OpenVCAD available?
Oh,
And
yeah.
I found your paper
Yeah,
in Elsevier. Yeah.
yeah, yeah, and then somebody just dropped in the link to the.
He
the
did,
public
he
wiki.
found it.
Yeah, great.
Cool. Wow.
Cool, all right, yeah, thanks. I know the
Fascinating.
room's booked right now, right?
In 2 minutes, yeah.
Okay.
I wanted to go on about how you write fitness functions to do these things, and, you know, you started with, I want something that's fast and light, and sort of, I want something that grips, but can grip an egg. I mean, sort of, how do you write those? I
Yeah.
guess that's future work.
It totally is. So I've kind of kicked the can down the road, right? Like I've tried to release the designer from needing to intuit what the design looks like.
Yeah.
Now the designer needs to intuit what the function looks like.
Yeah.